one thing that students have a huge problem with are sine curves and how to interpret real life situations, or at least in a math book. You can have sine curves representing anything that repeats in a pattern. I'll give you some examples in life where we would use sine curves. Okay, let me just make this bigger. Weather is a good one. And actually, let me just zoom in a bit so that you can see this. Weather is a good example. Tides. Anything in a 24-hour period. Anything in a monthly, but that's got errors because the months shift slightly. Anything like a pendulum. A wheel, so a car speed or bike speed, or sound frequency. These would all use sine curves. And that's because if you look at a sound wave, it looks almost identical to a sine curve. And I believe amplitude and wavelength change depending on loudness and frequency, so pitch of the sound. So all of these things actually do have world related things. Also light follows the same pattern as a wave. So we get information from the sun by studying changes in the frequencies. This is a wheelchair question, and it's determined. It's not a wheelchair, sorry, Ferris wheel question, and it's determined by this equation. So clearly this has a domain issue. It goes on from 0 to 40 seconds. And you have to get very good at understanding transformations of sine and cosine. And for that matter, you need to study the basic y is equal to sine x. And you need to understand the 5 basic points of a sine curve. So I encourage you to do that. So step 1 would be study the sine curve. And study it such that if you're in radians, which you should be in this grade, understand that there's 4 major points. I'm going to actually switch the degrees to pi over 2. There we go. Oh, that should not be on the x-axis. That should just be there. It should be on the the y. It should be on the x-axis. There we go. There are 4 major points: 0, 0, pi over 2, 1. So in other words, 90 degrees. The sine result. That's what the y-axis is. If we punch in pi over 2 in our calculator in radians and press sine, we will get the result of 1. If we punch pi into our calculator and press the sine button equals, we will get 0. Then down here, 3 pi over 2 is the same as 270 degrees. It's another half pi further from pi. And if we punch that into our sine, if we hit sine equals in radians, we'll get -1. And then finally you come back full circle, 2 pi, 0. If we punch 2 pi into a calculator, press sine, press equals, you get 0. The y-axis measures the sine result. The x-axis measures the angles in pi radians. Studying this is key. You also have to understand it's cyclical. Sorry, it follows a cycle. So every period, these values will repeat. Add pi to that, you get 5 pi. Or add 2 pi to that, because the period of a normal circle, that's another thing you need to know. The period of a normal sine curve is 2 pi. It follows a circle. A circle's circumference, if the radius is 1, is 2 pi r. When the radius is 1, it's 2 pi. And it repeats every 2 pi. Now that will change as we change the period of these things, and that will change also the results will change if we change the amplitude of these things, and the results will change if we transform the height of these things. For instance, if I add +2 to this, the whole thing climbs by 2. My axis is now y is equal to 2 instead of y is equal to 0. It's very important you understand all the transformations. If I put a 2 in front of this, my amplitude now goes up to 2 and down by 2. Now that doesn't mean if you punch into pi over 2 in your calculator, you'll get 2, you'll still get 1, but then you have to multiply it by this 2 over here, and you will get 2. It's very important that your calculator will only give results between -1 and 1 for sine results and cosine results. The transformations here are applied afterwards. Just like transformations of any other function, you would multiply your result by this 2 afterwards. It's very important you get comfortable with sine and understanding how to punch sine into the calculator, and also arc sine. So arc sine is something like this. If I give you a value of 0.8666 and I tell you that is the sine value for an angle, what is the angle? Well, first thing you have to say is that's a positive result. And looking at cast, I know that sine will be positive in this quadrant and this quadrant, which means I'm going to find, I'll get rid of these because they don't matter now, which means that when I find the result of this angle, I'm going to find initially always the calculator gives me quadrant 1. And how do I find that? Well, if sine of this angle is equal to that, you have to hit arc sine on your calculator. You have to punch in this number, hit arc sine, and it will spit out this angle. Now, if you want the angle in radians, make sure your calculator's in radians. So when you're dealing with pi in advanced functions, you have to have it in radians. And be careful, it'll spit out a number, and I'll show you how to convert that to pi radians. If you want to do it in degrees, that might be easier. Just remember that you then have to convert your degrees to pi radians by multiplying by pi, or just leave the pi like that, and divide your degrees by 180, and you will get it in a number pi radians. Let me show you both. And remember, we're just finding the first degree here. So 0.866666, whatever, and I'm going to do arc sine. So I got to go to second function on this calculator. I got to go to trig second function and do arc sine. And it's going to, notice I'm in radians. I'm going to start with just degrees. So I go to trig arc sine. And suddenly I discover I'm dealing with 60.07 degrees. So I'm going to forget the accuracy for now. So that means I'm dealing with 60.07 degrees. If I were to divide that by 180 and just cancel out my zeros, okay, I'm now dealing with that. If I divide this by 6 and this by 6, I'm getting roughly that. And that would be in pi radians. So it would be the fraction 1.07 over 3. And that's not quite accurate because when I divided by 6, I should have divided this by 6 as well. But it's roughly 1/3 pi radians. Let me go back to that. So when I punched in the calculator, I'm just going to hit sine to get back to it. I had this value and I was trying to find the angle. So I went to trig and I defined arc sine. That spat out the degrees. I'm able to convert this. Let's look at the accurate conversion into pi radians by multiplying it by pi over 180. But let's just leave the pi there and move the 180 over here. Well, if I divide both by 10, I get 6.07. This decimal moves over. If I divide this by 10, I get that. To convert it even better, I have to divide both numbers by 3. So I should really divide this by 3 if I divide that by 3. However, you could leave it like this as a fraction, and that would be very accurate. And that's 6.0733 over 18 times pi. It's just tough to put that in a calculator. Now, obviously in a test, he's just going to make it, it's just going to come out as 6 over 18. And when you divide by 3, you get 2 up here. When you divide by 6, you get 1 up here and 3 down here. And you'd be left with 1/3 pi radians. Obviously, in my example, I've come up with a weird degree. But this is how you would convert if it came out as 60 degrees into pi radians. If that 60 comes out, simplifies to 1/3 pi radians, which is the same as pi over 3 radians. We just never write the radians. So that's your angle. Now pi over 3 happens to be 60 degrees, but this is how it's written in arc. Now, let us say, though, we had some weird thing, transformation, in the brackets. I'm going to go back. So that's the first angle. And let's pretend that we found 60 degrees, because my example was random. Let's pretend we found 60 degrees over here, which is the same as we found out as pi over 3. But remember, there's another angle over here. And that angle over here between the x-axis will also be pi over 3. But we're always, however, looking for what's called the terminal angle, or I think it has another angle, name for it. And to get that, we have to go all the way to here, which is 2 pi, or which is pi, and subtract that pi over 3. So really, this angle here in the red line is pi minus pi over 3. We've got to convert that to pi over 3, so that's 3 pi over 3. 3 pi minus 1 pi is 2 pi over 3, which means this whole angle here is not only pi over 3, it is also 2 pi over 3. So we found our answers for that question. What is the angle when sine is given us as 0.866 or whatever it was, and pretend it comes out as 60? The answer is pi over 3 and 2 pi over 3. Great. What about when we have something complicated inside the transformation? What if we had something like this, sine, and I had all sorts of translations going on here? What if I had pi over 10, and then the x was also translated 2 to the right? Well, and I told you the result was the same, 0.866, whatever. I'm going to look up 60 degrees so that we're technically working with the decimals of 60 degrees, okay? And I told you the result was this. Well, the secret here is not try to get yourself bogged down until you're comfortable. Just let u equal to the interior. Great. Then just simply find sine of u first. When will the sine of this angle, and you don't have to call it u. If you want, you can call it sine of theta, or there's theta actually, or sine of omega, or whatever you want. But I like u because it's a nice consistent replacement. So when we solve for u, again, we find out it's 60 degrees, or pi over 3. And we also discover, because it's positive, it's that other one over here in quadrant 2, 2 pi over 3. It's both those angles. Great, we've discovered our angles. We've discovered that u is equal to 2 pi over 3, and that u is also the angle pi over 3. And you just get rid of all your work for now. And you put these separate, and now you solve it by bringing what you replaced u with. All right. I'm trying to get to x. To solve for x, I kind of have to do reverse bedmass here. I see a bracket. So reverse bedmass says BEDMAS. So reverse says I have to look for subtraction and addition. And I see it in there. However, that's in a bracket, so I can't touch it. So there's none so far. Is there any division or multiplication? Yes, it's being multiplied by pi and divided by 10. So we're going to get rid of that by multiplying by the reciprocal on both sides. We can see that gets rid of it here. And over here, oh, I multiplied by the wrong thing on the right side. It's being multiplied by the reciprocal, which is 10 over pi. Over here, we can see the pi's cancel out. That's nice. Here we have 2 times 10 divided by 3, so we're left with 20 over 3, and we're just going to leave it like that. 20 over 3. So we've got now x minus 2 is equal to 20. Well, we can get rid of our brackets because we got rid of the thing bothering our brackets, so we're just going to add 2 to both sides. When I add 2, if I want to make it simple, 2 over 3 is the same as 6 over 3. So I'm suddenly got x is equal to 20 over 3 plus 6 over 3. which is 26 over 3. Now, they can't be divided, can they? 3 goes into that? No. Almost, but they can't really be simplified. I could simplify it in whole numbers. My x is equal to, 3 goes into that 8 times, 8 2/3. If I want to put in decimals, that's 8.6 repeated. So I have my answer. When I'm dealing with 0.6666, whatever I had, the x value in here that will achieve that is 26 over 3, or 8 2/3, or 8.66. This can be proven when you substitute it back. And let's say I take 8.666. It won't give me exact, by the way, because I'm rounding up. And I put it in for x here, and I subtract 2. Whoops, see, it did something wrong there. So I got 8.666666, and I subtract 2. I get that. I have to multiply by pi in the brackets, and then divide by 10. And I get that. Oh, I did something wrong there. So I probably did a minor calculation error incorrectly, because the result should not come out bigger than oh, I know what I did. I used 2 pi over. Let's use pi over 3. Pi over 3, sorry. And we now know, since it's pi over 3, the u in there is going to be equal to that. Did I use that already? Yeah. So I got to get rid of this 10. So I'm going to multiply by 10. Got to get rid of this pi. So I'm going to divide by pi on both sides, and these pi's will now cancel out. And I get 10 over 3. 10 over 3 Oh yeah, this works fine. My bad. So, because it's going to be a bigger, you'll see. Okay, so it's 10 over 3, so that's the same thing. And then I add 2, which is the same as adding 6 over 3. And that's so that I did make a small calculation. I get 16 over 3. That's 5 1/3. So let's just, yeah, so that's that one. So that's 5 1/3 is the answer for x to achieve that result. If you go back, right, 5 1/3, if you go back and put 5 1/3 in here, and I subtract 2, I get 3 1/3, and if I divide that by 10, I get 0.3333 pi. Now I would just leave that like that, and so I got now sine of that is equal to my angle, right? But what is that? That is 1/3 pi. So we just so if I click in now, I'm trying to see if 1/3 pi, and we already know the truth. It's going to give me what I want, times pi. And if I do if I do sine of that, now I'm in radians, so you got to switch to radians. And if I hit sine of that, sure enough, I get the result that we started with. Sorry for all the confusion there. Now I can do the same thing for, I found out that it was 2/3 pi. And I found out 2/3 pi was one of my answers, so I make it equal to pi over 10, this interior. X minus 2, multiply by 10 on both sides. I get 20 over 3. That was my mistake, is forgetting that I'm actually in radians. Is equal to x minus 2. And you actually, yeah, you could, but it's, yeah, okay. Let's continue. Remember, that's the result we're looking for. So x minus 2 is equal to 20 over 3 pi radians. Oh yeah, that's right. I have to divide by pi on both sides, so the pi's cancel out. So x minus 2 is equal to 20 over 3. So 20 over 3 plus 2, which is the same as 6 over 3. So this one is 26 over 3. To figure out if I got the right one, I plug it back in. 26 over 3 minus 2 is the same as minus 6 over 3. I get 20 over 3. Divide by 10. So that gets divided by 10. I get 2 over 3. It's quite clear. 2 over 3 pi is exactly going to give me a sine value of what I'm looking for. So 2 times pi divided by 3 equals, and what's the sine of that? It gave me the exact value I started with. So that's how you know you got the correct x values, is when you plug it back in. But your step 1 is finding sine of u, and then replacing, once you find u, replacing it back with the original equation and solving for x using reverse bedmass. Once you find your x values, you should find 2, because there were 2 angles. Go back and verify that you got it right. Now, as you've seen, you can make a lot of arithmetic errors. Also, when you're given a formula, and in this Ferris wheel, in this Ferris wheel 1, we're given a formula right there. I'm going to copy it over. You should understand what the transformations are. So this one affects the period. This one affects the amplitude. So we know right away we've got an amplitude now that doesn't go up to 1. It goes up to 40. Now, this would not be technically a good Ferris wheel unless they dug 40 meters into the ground. But let's pretend it's a funky Ferris wheel that goes into a haunted house in the bottom part. And actually, that's a great idea. I should design this Ferris wheel. And otherwise, you'd see a plus 40 here to raise the whole Ferris wheel above the ground, or even plus 41, so the bottom of it doesn't hit the ground. For this Ferris wheel that I've done here, it's going below ground, so it doesn't really matter. So ask yourself, that's changed the amplitude. So right away, you know you have a Ferris wheel that goes 40 up and 40 down. How tall is that Ferris wheel if it goes 40 up and 40 down? It's 80 meters tall. So if they ask how many feet off the ground are you? Well, 80, unless you bury it in the ground like this one. So again, I should have added an alteration here. Any number here simply raises the whole thing off the ground or up and down on the y-axis. This affects the period. This affects the horizontal translation. So this thing is not moving to the right by 0.4. This whole graph is moving to the left by 0.4. And we're not sure the significance of 0.4 until we figure out the new period. Well, a normal period is 2 pi. Ignoring this transformation, this new period is pi over 10x. If I move the 10 over here, I get 20 pi. So I get pi x is equal to 20 pi. If I divide by pi on both sides, I get x is equal to 20. So that means the period went from 360 degrees, or 2 pi, to this unit like 20 seconds, 20 minutes, whatever the Ferris wheel takes to go around. By the way, at that period, 20 seconds to go around an 80-meter tall Ferris wheel, this thing's creating whiplash. So it's probably 20 minutes. But whatever. The new period for this whole thing to complete one cycle is no longer 360. It's 20, whatever the new units are. So let's say it's minutes. That means this shift here is 0.4 minutes to the left. In other words, the Ferris wheel doesn't start at the bottom. It's going to start somewhere over here. Transformations. Understand your transformations. So now, let's say you're given this as a puzzle. A person gets on a Ferris wheel at the height of 5.43. So that's what that left transformation did. It created an entry point that's off the ground here. It should be minutes. I put seconds because it's going crazy fast at seconds. The person exits at the ground level, so they exit over here. At what times are the person at the height of 20? And then it says, get rid of all this. What is the rate of change? So this second part is calculus. This first part is functions. So if you look at this thing, I've drawn a line through in green at height of 20, and it's clear they've gone through 4 times. The nice thing is you only have to figure out these first 2 times, and then add 1 period. Do you remember what the period was? We figured out the period of this was 20 seconds. So if I add 20 seconds to this, I get the next time he's at the same spot going up. And if I add 20 seconds to this spot, I get that spot the next time he's going down. So you can see this was set 7.93. When I add 20 seconds, it's 27.93, and so on, and so on, and so on. So remember that every period, these 2 points will repeat. So you really have to focus on the first 2 points, and that's all part of functions. Okay? Now, let's look at how you figure out the question step by step. You can freeze frame this and just figure it out yourself on your own time, okay? 1, make your equation simpler. So replace this really messy thing with u. Makes your brain less frazzled. Till you get comfortable with solving equations like this, just solve for u first. So let's say we're talking for a height of y, or 20, and we know that's on the y-axis. And I know normally you're going to see f of x, but I've just put it into y to make it simpler. So that means that when y is 20, we're going to figure out u. Okay, so we put 20 on the left and 40 times sine of u here. So that means we have to divide by 40 on both sides. So we get 20 over 40 is equal to sine of u. So that means half is equal to sine u. And we could hit our calculator and hit arc sine for a half to get the angle. Fortunately, we know from our exact angles that this is 30 degrees, or no, it's 60 degrees, I think. Let's see, 0.5. But you could. Let's do it. 0.5. And we're going to stay in degrees, though, just for now. And we're going to hit arc sine. So now, let's try it again. I think we're in rads now. Now that's saying to switch to rads, so it's kind of confusing. But if we hit 0.5 now and go to arc sine, it's not working out for me. Let's try again. .5. Trigonometry. Second thing. Arc sine. There we go. 30 degrees. So that's working with 30 degrees. Now, here's the problem, though. If we work with radians and we hit 0.5, you're not going to see it in pi's. So go second, arc sine. You're going to see it in decimal radians. And to figure that out, how many pi's is that, you essentially have to divide it by pi. Oops, it didn't really do it for me. Let's try that again. We're going to take 0.5. We're going to find the second thing, and we have radians, okay? And that's not going to help me figure it out. I have to take that and divide it by pi, and suddenly hit equals, and suddenly I get 0.16666. And as a fraction, that's hard to figure out unless you flip it upside down. Then you realize, oh, that's 1 over 6. So the problem with using radians on a calculator is it's going to spit out the decimal version of radians. And to figure that out in how many pi's is that, you have to divide it by pi. And it's not always going to be clean. And it still will always flip out a decimal. But whenever you want to see if a decimal, it makes a pure fraction, just flip it upside down. For instance, 0.33333, if I flip upside down, makes a pure, I rounded it up, but it's pretty sure it's 1 over 3, right? So what if you had something like, I'm going to take 3 and I'm going to divide it by 2. I'm going to take I'm going to take 1/3, actually. And I'm going to divide it by 2, and I'm going to divide by 2, and divide by 2. So it's quite hard to see that that's a fraction, isn't it, until I turn it upside down. And then I see that it's 1 over 24. So you can always figure out a decimal if it's pure in fractions by just hitting the reciprocal button. And you'll discover, oh, wait a minute, that's just 1 over 24. So I would write that as 1 over 24 pi or whatever I'm trying to figure out. In this case, we had this weird number here in radians because we solved 0.5 in radians for our sine, and we had this weird number. And when we divided it by pi, we had a weird number still. But then when we flipped it upside down, we realized, oh, that's 1/6 pi. Alternatively, you could figure out as we did. We figured out it's 30 degrees, and you can convert 30 degrees to pi's by multiplying by pi and dividing by 180, 0, 0. This divided by 3 is 1. This divided by 3 is 6. We get 1/6 pi's. So it's very important that you get comfortable doing that and what those numbers mean in your calculator. So there's two directions, right? There's sine. When you have the angle and you press sine, you get a decimal representation. And when you hit arc sine on the decimal representation, you get the angle. But if you have it in radians, it looks like a decimal again. So just make sure you really understand the directions of sine versus arc sine. And then I put a note here. Fortunately, we know from our exact values that this angle, when sine u is 0.5, the angle we're dealing with is 30 degrees, or pi over 6. But if we didn't know, we would take arc sine. At this point, we find the value of u. Please note, since we are working in pi, convert it to something over pi. Find it in degrees and multiply it by pi over 180, or find it in radians and divide it by pi to get a multiplier of pi radians. Otherwise, you'll be working in the decimals, and if your teacher wants to see an answer like this, you're not going to get full marks unless you learn how to convert. Before we continue, now that we know that we're dealing with the angle 30 degrees, or pi over 6, before we continue, go back to your result and realize that sine u 0.5 is positive, and ask yourself, cast, where is sine positive? Well, we determined it's quadrant 1 and quadrant 2. Therefore, there's two possible angles where sine of this angle is 0.5, which makes sense because on the Ferris wheel there's two possible heights. Going up, hit 20 meters, coming down, hit 20 meters. And that's true for any sine. If I draw through it and just do one cycle to see it, if I draw through it, I'm going to hit 2 points, except at the x-axis. At its axis, I will hit 3 points. But everywhere else, I will hit 2 points. You might say it's 3 points there, but yeah, I just didn't draw the period completely. If you do it correctly, if you draw it correctly, anywhere you draw a line will cross the sine axis twice, which explains why there's two possible angles. It's because there's two possible y values that cross that sine. Since we know it's 0.5, we know we're dealing with pi over 3, but we're also dealing with this other angle that is also pi over 3. And we determine that that's 1 pi minus pi over 3, which comes out to 2 over 3 pi. Therefore, we're dealing with two angles. So it goes through this explanation in red. Feel free to pause and just write it down. Oh, sorry, pi over 6 instead of pi over 3. We're dealing with 5 over 6 pi. So it's just good to be able to understand that we're dealing with two angles. Now that you know you have two possible angles where u is pi over 6 and u is pi over 6, 5 pi over 6, now you can go back and replace your u again and solve for both. So let's look at what we did there. So I know that u is equal to pi over 6. Now I bring what u is equal to, and I say, well, then this must be equal to pi over 6. I multiply. I've got to get x all alone, so I have to multiply by 10 and divide by pi. Or I could just multiply it by 10 over pi. That's the reciprocal of this to get rid of it, and multiply by 10 over pi here. The pi's cancel, and I'm left with 10 over 6, which is the same as 5 over 3. 10 over 6 is also 5 over 3. So I'm left with this. Now, clearly, I have to add 0.4 to both sides. Get comfortable with your algebra, too. 0.4 to both sides, and I discover x must be 1.627 seconds. X is this, and I know it's in seconds, even though it's way too fast. And that is our first height, and it occurs at that. Now, I also know it happens 20 seconds later at 21.627, but we'll get to that in a second. Calculating the other one, you do the same thing. You set your u, you replace your u, and you set it equals to this, and you solve for x, and you determine 7.93 is the other x value. So you can see this is our second height at 20 meters, occurs at 7.93. You can prove this graphically by going to Desmos. But wait, we have to realize the ride goes on longer. He gets off 39.6 seconds later. So we have to know that one complete cycle of the Ferris wheel is. That is held in this part, the transformation of the multiplier. So again, here's showing you how to figure out the cycle is 20 seconds. So that means the sine curve repeats after 20 units, in this case, seconds, no longer 2 pi. Since the height is reached twice in the first 20 seconds, we have to find 2 more heights, because this thing goes on for 40 seconds. So there's these 2 heights we figured out, but we need to figure out these 2 heights by simply adding 1 period to the previous values. Since there are 2 more times, we simply add the period to our first 2 times. One was 1.26, so the other was 7.93. So adding 20 to both gives us 21.26 and 27.93. So that is our other 2 times. These are our 4 coordinates. They all have a height of 20, and graphing will confirm this. The calculus part asks, how fast are they going up? So the rate of change of any position is a derivative, so you can stop the video here, because I just wanted you to get used to the first part. However, rate of change is something you're going to have to get used to. We're going to have to learn how to take the derivative of sine, and in this case, the derivative rule is we take the derivative of this and the derivative of the interior. The derivative of the interior, I just make it u. It's very easy to rewrite it as u again. So our derivative will be saying we're going to find the derivative of sine u and the derivative of the interior, which is this part. You're going to learn that the derivative of the interior is simply that. But we're going to go on. We're also going to learn that the derivative of sine is cos of the same value. So that means the derivative of this is 40 cos of whatever u is, times pi over 10, which is the derivative of the interior. But we'll get to that. Again, stop. This is calculus. We're not there yet. I just wanted you to get used to solving complex trigonomic equations backwards. The derivative of sine x is cos x, and when there's a transformation, you need to multiply it by the derivative of the interior. So that means the derivative of the interior is that. We will get to that, how to figure that out. And therefore, the derivative of 40 sine u is equal to the derivative of sine u times the derivative of u. The derivative of 40 sine u is 40 cos u, and the derivative of the interior u is pi over 10. Therefore, this is the derivative formula for finding how fast that Ferris wheel is going up or that Ferris wheel is going down at any point of x. But we've got to replace this u over here. So now if I said at 2 seconds, how fast is he going? I can put in 2 here, do 2.4, multiply it by pi, divided by 10. Take the cosine of that, then multiply it by pi and 4, and I will see how many meters per second he is climbing at 2 seconds. Fortunately, we did find out the 4 x values for this particular situation. We found out the x values were right there. We simply plug them in for x 1 by 1. Remember that this is a cos of that, not the sine. And also remember that you have to plug in x here, add it to 0.4, multiply it by pi, and since we're in pi, we're in radians, divide by 10, switch to radians before you press the cos equals sign, then multiply by pi, which is a multiplier out here, and multiply by 4. How did that pi get there? It was the derivative of pi over 10 here. How did it become 4 pi? Well, we had 40 here, and actually that should be, yeah, we had 40 here times the pi of 10, cancel the 10s, and I get 4 pi. That's where that 4 pi came from. And once I go through all that, and I outline the steps below, I do it here and show the steps, and then remember, switch your calculator radians. Then I have to take the cosine of that. I get this. Then I multiply that by pi and by 4, and I get 10.822 meters per second. And that's why I say this ride's too fast. It should have been in minutes, because that's about 40 kilometers an hour. That ride's whipping. So the rate of change is 1.26. At 1.26 is 10 meters per second. Now, fortunately, the third x, the one that happens one period around, is going up at the same angle. So the third value at 21.26 will be the same thing. And that just takes time and practice to realize it. But let's find the second angle. You do the same thing. You plug it in for x. You add 0.4. You get 8.333. You multiply it by pi, divide by 10. Make sure your calculator's on radians and press cos equal. And you get this. I've got it here. And then you get this value, negative 0.866. By the way, is the negative of this one we got up here, which makes sense because if you look at the ride, he's going to be coming down just as fast at that same height as he was going up. So it makes sense. And if you don't get the same value at the same height but reverse direction, why is it negative? Because he's going down now. His rate of change is he's falling at that fast. And then we get he's determining that he's indeed this time going negative 10.822 meters per second, which makes sense. However, it's breakneck, and therefore also at 7.93, he is also going negative 0.29 meters per second. Don't expect you to do the blue. The blue is the next level. However, it's very good to get good at these because you will find endless questions like this. It's fantastic to break your U down in the interior. Sorry about the confusion in the beginning. I just had a minor brain fart. But it is very smart to break down your U into your angle, your interior transformation into just U. And treat that like the angle you're looking for. Makes it so much easier. All right.